Okay, today I'm going to start a new chapter, that is sampling. Sampling. So as far as we have discussed about the signals and systems, and after that Fourier series and Fourier transforms, okay, which are related to the signals and the systems, right? So these are the two topics, two chapters what we have discussed so far. Now, this is a very easiest chapter among the six chapters. So you have only six chapters in this particular subject, signals and systems. Out of six chapters, we have completed two chapters in all aspects. In all aspects, and the third one is sampling. This is also very easiest chapter among all the six chapters. So I require four classes to complete this chapter. So as soon as the chapter has been completed, I shall forward the material to your WhatsApp group. So you please find the links also, YouTube links also in the Google Drive. I think your class teacher will circulate those links to you. Okay. So if anybody is absent or if anybody is unable to attend the particular session, so you can able to find out those sessions in your YouTube links. Okay. Now sampling. Let us quickly start our actual topic. Uh, Now, before going to discuss the topic, first of all, I want to share the screen to you. So now I am sharing my screen here. Now, please, anybody respond. Is my screen visible?
Yes, sir.
Anyone? Okay. See, now I am showing the PowerPoint presentation here. Please,
Yes, sir.
you please see here. Okay. Now, is it okay? Right. Now I am taking the complete control over this session. So you don't have any right or you don't have any control over for muting or unmuting yourself, right? Now let us discuss in brief. Right, sampling. Now what is sampling? Why we require or why we need to study about the sampling in particularly in signals and systems? Our digital signal processing is also there, digital control systems is also there. See, nowadays we are very much familiar with the word digital. Okay, everywhere we can find digital India. Okay, digital word is very important. So that is why we are learning the concepts of signals and systems and digital signal processing in our engineering, so that we can able to apply the applications of the subjects what we learned in this engineering in our regular or daily engineering applications, right? Sampling. What is the need of sampling? Before going to that, first of all, what is defined sampling? Definition. What is the exact definition of sampling? Sampling is nothing but the process of converting continuous time domain signals to discrete time signals. Once again, please remember the basic definition of sampling. Sampling is the process of converting the continuous time signals to discrete time signals. Whenever we are discussing chapter number 1, there I have given you the mathematical expression for converting the continuous time domain signals to discrete time domain signals. Okay. Once again, it's my responsibility to uh, recollect the contents what we have discussed in chapter number 1. Now see here. So here x of t is a continuous time domain signal. X of t is a continuous time domain signal. Now, as far as the knowledge we have gained by studying the chapter number 1 and chapter number 2, the discrete time signals are always represented with the x of small n, and the continuous time signals are always represented with the x of t. Okay, now the process of sampling is conversion of this analog or continuous time domain signals to discrete time domain signals. Now, what is the fundamental equation or mathematical equation for representing the same? The same. That means, so you see here. So here x of n into capital T, x of n into capital T. See, both are same. X of n or x of nt, both are same. So which is equal to x of t, which is equal to x of t at time t is equal to n into t. Now this is the mathematical expression which we are using for converting continuous time domain signals to discrete time signals. Discrete time signals where this small n represents the discrete time index and the capital T stands for the sampling time period. So at what time you are going to sample? See, sample is nothing but suppose here you are having a sinusoidal waveform, that to continuous time domain signal. So this is x of t, x of t, x of t. Sample is nothing but, now see here, I am drawing a line onto the x-axis, from a certain point. That means here at this particular instant of time, I am going to measure the magnitude of x of t. So here this is a sample. Sampling is nothing but the process of measuring the magnitude of the particular x of t at a particular instant of time. See, as we all know that x of t is continuously varying with respect to time. Continuously varying with respect to time. So in between 0 and 1, you will have infinite number of values are existing, but that is not in the case of discrete time signals. So discrete time signals are always represented or defined at a are defined at a prescribed instance of time or predefined instance of time. That is the basic difference between continuous time domain signal and the discrete time domain signals. Now here n is nothing but an integer. N is nothing but an integer. So 0, 1, 2, etc. and up to infinity. Now if I have given you the sampling time period t is equal to 0.2 seconds, 0.2 seconds, and x of t is equal to a sine waveform. See, already we have solved the same example in chapter number 1 itself. Chapter number 1 itself. But in that particular instant of time, I have not discussed much regarding this sampling process. Okay, so in detail, the sampling process is going to be discussed in this particular chapter. Okay, so whatever may be the contents that I am explaining, see, already these contents have been seen in the chapter number 1, right? So sampling is nothing but, the basic definition is, sampling is nothing but the process of converting continuous time domain signals to discrete signals. See, what is the need or why we need to convert the continuous time domain signals to discrete time domain signals. For that for that I need to explain one simple example related to our electrical engineering field, or our electrical engineering. Now, I think in your laboratory we have two types of devices. The first one is analog multimeter or digital multimeter. See, I think you have learned or you hear these particular names in your laboratories. That may be either electronic laboratories or machines laboratory also. Okay, so already you have studied the measurements also. Okay, measurements, electrical measurements. In that particular subject, we have learned the basic principles of MI meters and MC meters. MI meters and MC meters, AC meters and DC meters. Suppose if you take a moving coil voltmeter, MC voltmeter. So for MC voltmeter, again, you will have two types of devices that are existing for measuring voltage in DC circuits. The first one is digital voltmeter, second one is analog voltmeter. What is the basic difference between digital and analog? See, whenever you are having a rotatory parts for measuring the voltage or current or power, whatever it may be, all those meters are comes under analog devices. Okay, but while considering the digital devices, you should not have any moving parts. You will have only LCD 7 segment display. The numbers are displayed on the multimeter or ammeter or voltmeter or whatever it may be. So that is the digital multimeter or digital voltmeter or digital ammeter or digital wattmeter also. So whenever you use the word digital or discrete, see already we have seen the basic difference between digital signals and discrete signals. Discrete signals are also named as digital signals if it is quantized in magnitude. What do you mean by quantization? Basically, now see, digital signals, digital and discrete signals. See, these are the two types of signals. Okay, looks like same, digital signal or discrete signal, both are same, but where we will find the basic difference between these two signals. Discrete signals are also termed as digital signals once if we are taking the quantization in magnitude. Quantization means, again, quantization is a process of rounding off or truncation of the digits. Rounding off or truncation of the digits. So rounding off means we should, suppose if it is 3.56, we should round it off it to nearest integer value, that is 3.6. 3.56 will be rounded off to 3.6 or 3.567. So it will be rounded off to either 3.6. If you want, you can round it off to 3.6 or 3.5 also. You can keep as it is, no problem. Don't worry about it. Okay. Truncation means 3.567. So you should truncate the last two decimals. So 6, 7 will be eliminated. Only 3.5 is there. That is the process of truncation. So discrete signals are quantized in magnitude, can be treated as digital signals. So basically there is no big difference between discrete and digital signals. Only quantization in magnitude is there. That is the point. Okay. Now, so what is the need? Why we need to convert the continuous time domain signals to discrete signals or digital signals? Nowadays, main important point here is all the components are replacing with the digital equipment. Digital equipment. So once upon a time, okay, to have cable TV, we will insert the antennas on the top of our building. But nowadays, entire the process has been changed. So completely, the digital TVs are also available, and the cable networks are also digitalized. So everything in every application, we are mainly focusing on the digital, digital. So digital devices will accept not analog signal, will accept only digital signals. Digital signals. Okay, it will not accept the analog signal. So that is why we need to convert before being processed to the circuit. So first of all, we all the available signals are continuous, no doubt at all. All the available signals are continuous time signals only. All the available signals are continuous time signals only. But here you will have one step before going to proceed to the digital device. That step is, first of all, A to D converter is placed. A to D converter, that means analog to digital converter is there to convert these analog signals to digital signals. So like MC meter does not works with AC signals, right? So always MC meters, MC ammeter, MC voltmeter are connected to DC supplies, not for AC supplies. If you connect a MC meter in place of MI or MI meter in place of MC, nothing will happen. Nothing. Don't, please do remember, nothing will happen. The meter does not works at all. The meter does not works at all. Why? Because the principle of working is completely different for MC meters and MI meters. Likewise, also in this particular case, you will have digital devices available or analog devices are also available, but we are mainly focusing on digital devices. So digital device will accept only digital input and it will use only digital output. That is the first thing you need to remember here. Okay, so you will find a lot of our extensive applications of the sampling process in digital signal processing. Okay, so if you want, you can type the sampling applications in Google. You will find a lot of practical applications. Everywhere you can find the applications of sampling. So that is why, first of all, it is very important to learn what is the importance of sampling in any engineering field. Okay, now let us continue our session. Now please see here the first definition. Just now we have discussed that the process of converting continuous time domain signals to discrete time domain signals is called sampling. So it is the process. Okay, already we have seen the mathematical expression also. X of nt is equal to x of t, where t is equal to nt. And at the same time, see, only for or only to make our analysis is simple, we are calculating or we are going to convert the analog signals to digital signals. Later later it is very important to get the, see, suppose if I have given you x of t, now that x of t has been passed to d to a converter or a to d converter, and after that that analog signal has been converted to digital signal, and that digital signal has been processed by a digital signal processor. After that you will get digital output. Later again you will get the output in terms of analog. The first and very first point is, just wait a moment. Okay, see, the first and foremost important point here is you need to get the original signal even after the conversion. Like the topic already we have discussed in the last chapter. What is that? X of t and x of j omega, x of omega is the Fourier transform pair. So if you consider x of t, then x of omega is a Fourier transform of that function. Even if you consider, or even if you take the inverse Fourier transform of x of omega, definitely you should get x of t. No doubt at all. See, original signal has been reconstructed as it is. So the signal reconstruction must be very important here. We should not lose the data in between any two successive samples. So that is the point here. The sampling rate must be kept higher than the original, higher to reconstruct the original signal. So in order to get the original signal from the digital device, you should apply, or you should take the sampling rate. That means the sampling frequency must be higher. So you should select the frequency range to certain level, so that you can able to get the original data without missing any information in between the two successive consecutive samples. So that is a very important point here. Now see the mathematical formulation. So just now we have discussed about the block diagram. See, now see here. So this is x of t, which is the basically available continuous time domain signals. Now this has been given to sampler. So what is a sampler? In the sampler block you will have a to d converter. Okay, so after that, what is the output you are getting? X of n into t. You will get x of n into t. Now this has been digitalized. The available signal x of t has been converted to x of nt by using sampler. And after that, the quantizer plays very important role. So what is the quantizer? What is a quantizer? Quantizer is nothing but the process of quantization. So which consists of two parts. The first part is you should round off the value. You should round off the magnitudes, or you should truncate the magnitude also. Round off the magnitude is different, truncation is different. Okay, now please see what is the difference between round off and the truncation. See, 3.67 round off round off value is 3.7. Round off value is 3.7. Now what is the truncation? Now 3.67 is truncate. by 2 decimals. So what is the value? So the value is, just wait a moment, 1 decimal. Now the value is 3.6. So this will be trunk off. This will be trunk off. So this will be trunk off. Only you will have 3.6. Now that is the process involved in the quantizer. And now what is the output you are getting from the quantizer block? See, block diagram technique is very well known to you. Why? Because already you have learned these block diagram techniques in your control systems, right? So for easy understanding, we are representing that sampler block. See, sampler, when you double click on that sampler block, you will get A to D converter, detailed diagram of A to D converter. But we should not bother about that. Why? Because block diagram technique is like that only. So quantizer is having a separate circuit, and decoding is also having a separate circuit. So at finally, you will get digital output from the main digital signal processing. See, the combined three blocks will gives you are is nothing but a digital signal processor. Digital signal processor. Okay. So whenever, now please see. So whenever I write DSP block here, DSP block here. So DSP includes sampler, quantizer, coder. So when you double click on this, you will get these three blocks. So if you double click on the sampler, you will get the internal block diagram of that sampler. If you double click on this, obviously you will get the same thing. Okay, right. Now this is the basic block diagram of the uh, sampling process. Now see here, here I have marked a very important point, that is if capital T is the time interval between the successive samples. See, I forget to write or draw the samples here. Now see here, so always the samples are represented with an arrow like this. So this is x of nt. This is x of n into capital T. So this is n. Okay. Now t, 2t, 3t, 4t, 5t, 60, 70, and etc. up to infinity. N is equal to infinity. So n is varying from 0 to infinity. So this is the digital signal you have obtained from x of t only. X of t only. So without having the information of x of t, it is not possible to draw x of nt. Now see here. So here x of nt is equal to x of n. Both are same. Both are same. There is no difference between x of n into capital T and x of n. X of n is the direct discrete time signal, and x of n into t is the discrete signal which is applied or which is getting from the sampled continuous time domain signals. So if you sample the continuous time domain signal x of t, you will get x of nt. So that x of nt is nothing but your discrete signal x of n, and the range of n x of n is also given. I mean, n is also given, but n is defined from minus infinity to plus infinity. That means it is either a positive integer or negative integer. Don't bother. Don't bother about the value. So sometimes it is a negative integer, sometimes it is a positive integer. So this is the basic mathematical formulation of the sampling. Now see here, the time interval between two consecutive successive samples is called sampling time period. Now see here. So this is sample 1, sample 2, sample 3. For your easy reference, I am considering n is equal to 0 here. So n into t. So this is x of n into capital T. So this is a discrete signal. Please do remember. So this is 0 into t or 1 into t. So t. So this is 2t. This is 3t, etc. up to infinity. Now, what he has given? So the time interval between any two successive samples. Successive means so this one or this one, this one or this one, or this one or this one. So whatever may be the two samples, two successive samples, so you will consider the time interval between those two successive samples is equal to capital T. That is the sampling time period. So once if you take the reciprocal of that sample time period, you will get sample frequency. So that is called sampling rate. Sampling rate. So Fs is the sampling frequency or sample rate. Now, just he has explained with the mathematical equations. Let us consider, let us consider x of t is equal to sine omega t, and the t is equal to n into capital T. So definitely he will mention the sample time period also. At what time you are asked to sample the given signal. Okay. Now substitute t is equal to nt here. So what you will get? X of nt is equal to sine of omega into n into t. Just simply I am replacing small t by n into capital T. Now what you will get? So x of nt is as it is. Now this omega into capital T is equal to, I have taken that as omega. So now this is the omega. So x of nt is equal to sine omega n. Now this is the discrete time signal. Okay. So initially I have considered sine of now this one. Initially I have considered x of t is equal to sine omega t. Later after sampling process has been done, what I will get? So I will get x of n into capital T is equal to sine omega n, where omega is equal to pi into t. Okay, pi into t. So this is how you are going to convert the continuous time domain signals to discrete time signals. Discrete time signals. Now here one important concept will arise in this sampling process. Aliasing. What do you mean by aliasing? Time domain aliasing. I think you will listen this or you hear this word about aliasing in your I think in your mathematics, right? Time domain aliasing. Time domain aliasing. Aliasing is nothing but some type of distorted waveform. Distorted waveform. So some type of distortions will comes into the picture when you select the values of frequency. Okay, when you select the values of frequency. Now see, he has defined with some terminology terms. Aliasing is an effect that causes different signals to become indistinguishable or when it's sampled. It also often refers to the distortion that results when a signal reconstructed from the samples it is different from the original continuous time domain signals. Simple. It is a very very simple definition. Our main intention is to get the original signal from the obtained value or sampled signal. See, once if x of t has been digitalized, x of t has been digitalized, that means it has been converted, the output is x of nt. Okay, always there must be some scope for getting the original data as it is. Otherwise it is nothing. If you are not getting the original data from the system after conversion, there is nothing, no meaning for the sampling process, no need for the digital devices also. Even though we have converted the analog signals or continuous time domain signals to digital signals or discrete signals, but finally we should again reconstruct the original data without loss of data or without missing the data in between any two successive samples. Okay, suppose here I want to explain one easy example. Suppose if you are hearing a melody song in your iPod or a phone or from your whatever it may be, the device what you are using, you are hearing that melody voice. Is it a continuous or a discontinuous? Is it a continuous or discontinuous? We are continuously listening the song. There is no discontinuity at all. Now just imagine if there is any discontinuity is there. Discontinuity is nothing but we lost the data. We lost the data in between two successive samples. But the technology that what you have used is only digital technology. But the available signals are analog signals. You have converted that analog signals to digital signals. Now the digital signals has been processed by the digital device. And the later on, again, you are going to get the continuously you are hearing the song. There is no discontinuity at all. Please do remember, there is no discontinuity. You are continuously hearing, you are continuously listening the song. Now just imagine what happens if there is a breaks. What happens if there is a break? Break is nothing but discontinuity. That means in that particular time, you lost the data. You lost the data. So that is the example for explaining the concept of reconstruction of the original data. Reconstruction of the original data. So here, aliasing is also one type of distorted waveform. Distorted waveform is going to be occur if you want to regenerate or reconstruct the original data from the sampled values or from the sampled data. Okay. Now this is this is a very uh, important aspect you need to consider in sampling process, aliasing. So how to avoid this type of aliasing effects? Okay, so this is a main cause in sampling process. This is a disadvantage. Now how do we overcome this time domain aliasing? Now this, please see here. See, you will have aliasing filters. Time domain aliasing filters are also available. In that particular case, if you select the proper value for frequency, obviously you should be able to get the original data without having some distortion. That means without aliasing. See, this time domain aliasing is also clearly explained with the use of graphical representations. Now please see here. Please see here. So here the first one and second one, A and B, are the output of ADC produces sample for two inputs. So in the first case, I have taken one sinusoidal input, and in the second case, I have taken another sinusoidal. In both the cases, both are sinusoidal signals only. But in first case, the frequency is different, and in the second case, the frequency is different. So just with the different frequencies, I have taken the same sinusoidal signal, and I have applied those two sinusoidal signals as input to ADC. ADC means A to D converter, analog to digital converter. Now see what is the output you are getting from ADC? X of n. Now these are all called samples. Samples. Now you will have sample at 1, sample at 2, sample at 3, sample at 4, sample at 5. Okay. Now the two different sine waves having the same samples. In the next case, if these two sine waveforms, whatever may be the sine waveforms you have taken, are having same samples, now what is the case? In that particular case, so see here, just now I told you that frequencies are different. You are going to consider two sine waveforms of different frequencies. Here, one frequency, this is a 40 Hz frequency, case B, case A is 10 Hz signal. Now superimpose those two sinusoidal signals, and which are sampled at the same sample value. So here sample is sample values are given by 0, 1, 2, 3, 4, 5, etc. Likewise, in this case also you need to consider the same samples here. So at 1, now this is the case. At 2, this is the case. 3, at 4, at 5. So two different sine waves having same samples. Same sample means if the first sine waveform is going to be sampled at 0 means obviously second waveform is also going to be sampled at the same value. If the first waveform is sampled at n is equal to 1 means obviously second waveform is also going to be sampled at the same value. So likewise, you are going to have the same samples for the superimposed signals. So case 1 and case 2. Observe the case 1 and case 2. Okay. Absolutely, sir. Interesting. Okay. Now illustration of aliasing. Illustration of aliasing. So if you consider the sampling frequency f is equal to 30, like you see case number 3, that means C, 40 hertz signal, 10 hertz signal. So in between 40 hertz signal and 10 hertz signal, now I have taken frequency f is equal to 30 hertz signal. Now what is a sample and where do we take the sample? That is the very very important point you need to remember in the case of aliasing. Some type of distorted waveform. Distorted waveform. Okay. Now, at 10 is equal to 10 hertz, at 10 is equal to 10 hertz, you will have some distortion. So, whenever you are having some distortions, means it is not possible to get the original data. That is the point you need to remember. Okay. So, the next one is Nyquist frequency. What is the Nyquist frequency? What is the Nyquist frequency and what is the range of frequencies you need to select? Okay. Now just carefully go through this. If the sampling frequency is fs, so all signals of frequencies above fs by 2 cause aliasing. Nothing but you will have distortion. This can be avoided if the input signal frequencies is below fs by 2. This frequency fs by 2 is called Nyquist frequency and also called as a folding frequency. See, what are the causes of having the time domain aliasing? Suppose whenever the signal what you have considered is having the frequencies which is greater than fs by 2, where fs is the sampling frequency. So the signal frequencies of the considered signals which are greater than or above fs by 2 causes aliasing. Nothing but some type of distorted waveform you will get whenever you are regenerating or reconstructing the original data from the sampled values. So this can be avoided. So how do we avoid the time domain aliasing? See, this is a serious effect you should consider, you should focus on. Okay, so we should completely eliminate the time domain aliasing to get the original data. So how to avoid the time domain aliasing? So you can avoid the time domain aliasing by selecting the input signal frequencies is below fs by 2, below fs by 2. So this frequency fs by 2 is nothing but the Nyquist frequency. So always you should select the input signals frequencies are equal to the Nyquist frequency, which is also called as a folding frequency. The other name for this is a folding frequency. Now see the last point I have mentioned here. If we restrict our spectral band of interest to the frequency range plus or minus omega s by 2, plus or minus omega s by 2, plus or minus omega s by 2 on the sample input signal with a sampling rate of omega s, then the aliasing can be avoided. If the highest frequency present in the signal is fm, then the sampling rate must be higher than, greater than, or equal to. See, just now I told you about the condition for eliminating the time domain aliasing. The condition for time domain aliasing or to avoid the time domain aliasing is fs must be greater than or equal to 2 into fm. Now you need to select the sampling rate of the input signal must be greater than or equal to 2 into the highest frequency content in the input signal, that is denoted with the fm. So how to avoid the time domain? See, this is a very very important bit also. In gate exam, sometimes directly you are getting what is the sampling frequency of the system to avoid the time domain aliasing. Okay, so you must select the sampling frequency or sampling rate that must be greater than or equal to 2 into f. Okay, so this is about the Nyquist frequency. Now see, there are different cases. Just now we have discussed about the to avoid the time domain aliasing, we should select the sampling rate that must be greater than or equal to 2 into. So here you will find three important cases. Three important cases. The first one, see case one. Now what is a given signal? What is a given signal? This is a continuous time domain signal which has given. Now this continuous time signal has been converted to this x of n, discrete signal, that means sampled signal. Sampled at a frequency, fs must be less than 2 into fm. Less than 2 into fm. So in this particular case, now just carefully observe the waveform. Now see here. Now see the sampling rates. So you have selected the sampling rate which is less than 2 into f. Okay. Now observe, is it looks like a sine wave or different other waveform? I think it is not related to sine wave. It is some other distorted waveform. So why? Because you have selected the sampling frequency that must be less than 2 into the highest frequency content in the signal. Okay, so that is why in this particular case we should not get the original data. So this is somewhat which is undistinguishable. Undistinguishable means which is a distorted waveform, distorted from the original waveform. So that is why in this particular case we should not get the original value. So if you see this second case and the third case, now in this case you have selected fs is equal to 2 into fm, and then the last case you have selected the sampling rate must be greater than 2 into fm. In both the cases, see, after getting the sampled data, in order to get the original data, you should reconstruct the data just with the use of samples. Now in both the cases, just these are looks like a sampled, or these are looks like a the signal what we have given. So x of t just looks like a triangular or sorry sinusoidal wave. Now see here. So if you have sine wave, you should clearly see. Okay, so just by seeing the figures, you can clearly visually see that. Visually see that the original signal is reconstructed. Now, in case one, it is not. It just looks like a original waveform x of t. But in case two and case three, just it is possible to get the original data from the sampled value. So this shows the Nyquist frequency. You should select the proper value. Fs by 2 is nothing but a Nyquist frequency, which is denoted with the Fn. Okay. Now we are moving into the next one is sampling theorem. Very important topic here. One of the important question in this particular chapter, sampling theorem. Now please see here. Statement. Sampling theorem. If you have pen and paper, you please just try to make a note. Theorem statement. Sampling theorem. A band limited signal x of t with x of omega is equal to 0 for omega greater than omega n can be represented. That means the Fourier transform x of omega is nothing but the Fourier transform. Okay, so band limited signal, you can take any band limited signal, the limited band. The band of frequencies has been limited, certain band of frequencies. So you should take that band limited signal, any band limited signal x of t with x of omega is equal to 0. That means the Fourier transform of that function is equal to 0. For omega greater than omega m, omega greater than omega n. That can be represented into and uniquely determined from its sampling x of n if the sampling frequency is fs greater than 2 into fm, where fm is the highest frequency component present in it. That means indirectly I'm going to say that you need to select the sample rate or the sampling frequency that must be greater than or equal to 2 into fm to get the original data or to reconstruct the original data from the sampled signal. Now, figure A. Now see here. Now see here. Figure A, which is a given function, a sinusoidal function x of t, and one complete cycle has been given. And in figure 2, you are having a product. That means you are going to multiply x of t with the a unit pulse impulse train. So this is called impulse train. Now this is up to infinity and this is up to minus infinity. But whatever it may be, this is a impulse train, unit impulse train. So that has been given as one of the input to the summer, and the next input is the original signal x of t. If you want to multiply this x of t with what you will get, you will get the sampled signal x of nt or xs of t, whatever it may be. So here the denotation, see the notation what we have used for sampled signal. Now x of t is a given continuous time signal. If we apply sampling to this continuous time domain signal, now that has been converted to xs of t, xs of t. Okay, that means sampled x of t, sampled value of x of t, or you should also consider that as x of n into t, that is a sampled signal or digital signal. Digital signal. Now, how it looks like? How it looks like? Now see here, just multiplication of x of t with the unit impulse train. Now see here, suppose if I have taken this as 0, so 0 into 1 means you will get 0 only. Now suppose let us consider this as 0.5. So 0.5 into 1 is equal to 0.5. Okay. Similarly 0.8 into 1. Similarly 1 into 1. Similarly 1.2. So whatever may be the function you have multiplied with impulse function, you will get the same function x of t. So that is why I have represented x of t with the dashed lines, and impulses has been changed. Okay, impulses has. So this is the sampled signal. So this is sampled signal. This is the sampled signal. Right. So this is the given continuous time domain signal, and this is the process of sampler. So sampler, and this is the unit impulse train, which is defined from minus infinity to plus infinity. And what is the resultant signal you are getting from the sampler? Now this is the resultant signal you are getting from the sampler. So this represents x of n into capital T, x of n into capital T, right? Now let's move on to the next one. This is a very important question. State and explain in detail about the sampling theorem. About the sampling theorem. Now see the proof. Here the proof has been given. X of t in a continuous time band limited signal to be sampled, which has no spectral components above the maximum frequency component. That means x of omega, the Fourier transform of x of t is 0 for omega greater than omega n, where delta is the impulse train which samples at a rate of frequency of the section. And excess. See, already these notations have been discussed in the last slide. Okay. So now equation 1. Now see the equation 1. Excess of t is equal to x of t into delta t of t, where the delta t of t has been denoted with this one. Summation n is equal to minus infinity to plus infinity delta of t minus n t. See, impulse train is the combination of infinite number of impulses, delayed impulses. See, summation means you should sum up all the impulses which are defined from minus infinity to plus infinity. Okay. So this is equation number 1. Now see here. So exponential form of the impulse function, unit impulse train is given by. Now this is exponential form. So this can be taken from the last equation number 1. So where where delta of t is equal to sigma n is equal to minus infinity to plus infinity into delta of t minus n into t. Now, according to the complex exponential Fourier series, okay, this can be equated to the complex exponential Fourier series. Now, I want to find out the Cn value. Now, where Cn is equal to 1 by t into integral minus t by 2 to plus t by 2 x of t x of t into e power minus j into n into omega s. Now, what is x of t? Here, x of t is an impulse signal. So, whenever you substituted that x of t is equal to delta of t, you need not find out the integration from minus t by 2 to plus t by 2. Why? Because delta of t is having value only at t is equal to 0. And for remaining values of time, that signal is not defined. So, that is why Cn has been approximated to 1 by t. So, if you want to substitute this one in this case, delta of t into t is equal to sigma n is equal to minus infinity to plus infinity. Okay, 1 by t into exponential e power j n omega s into t. Okay, just I have simply substituted Cn is equal to 1 by t here. Now, put this delta t of t in equation number. So, what is equation number 1? What is equation number 1? So, excess of t, that is the sampled value of the input signal x of t is equal to x of t into delta t of t. This is already we have seen in the case of the sample. So excess of t is equal to this one. Okay. Now simply substitute delta t is equal to 1 by t into this entire. Now you can take this 1 by capital T outside the summation because this is completely independent on the summation limits. So you can take that x of t inside the summation and x of t multiplied by exponential e power j n omega s into t. So if you consider the Fourier transform on both sides for this particular function, the Fourier transform on both sides. Now the Fourier transform of this function is equal to excess of omega and equal to Fourier transform of excess of t 1 by t into the Fourier transform of x of t into this one. Now what is the Fourier transform of this entire function? So already we have seen the properties. We have seen the properties of Fourier transform. So by using the properties, this is the frequency shifting property. Frequency shifting property of the Fourier transform. So according to the frequency shifting property of the Fourier transform, the excess of omega is equal to 1 by t. See the last excess of omega is equal to 1 by t into summation n is equal to minus infinity to plus infinity x of omega minus n into omega yes. So which is equal to 1 by t into omega. You should keep that omega as it is. But what is omega s? Omega s is nothing but the sampling frequency. Already we know that the sampling frequency is equal to 2 pi by capital T into n. Now this is excess of omega. So you should remember this final expression. If you want to note down the same, Just I will give you 2 to 3 minutes time for noting down the same. Just to go through the contents. Even though if you have any doubts regarding this explanation, you just ask your doubts without having any hesitation. So I will give you 2 to 3 minutes time for noting the same, because the next one, the graphical representation of the sampling process. This is also called as theory. Next, you will have impulse sampling. Now, the sampling theorem statement and the sampling theorem proof, what we did is also applicable to the impulse sampling. You should again extend the same version to impulse sampling also. Okay. If you have any doubts, you please raise your hand in a chat box so that participants I can able to give you the control for unmuting yourselves. Okay. Now see here. So this is the graphical representation for data reconstruction from the sampled value. Now here, x of j omega. Now this can also be considered as omega m. Don't get confused. In some textbooks, you will have this type of components, notations, and in some textbooks you will have this type of notations. But whatever it may be, this is the triangular waveform which is defined from minus omega m to plus omega m. So this is the Fourier transform of the given signal. Okay. Now here again you will have three cases. In case one, what happens? What happens if the selected frequency omega m is equal to pi by t, and if the selected frequency pi by t is greater than omega m, pi by t is less than omega. If you clearly observe these three cases, now see, whenever you are going to select the frequency omega m is equal to the maximum frequency value is equal to pi by t, in that particular case, you will get this type of waveform. Now carefully observe this waveform. Do you have any missing data in between two successive samples? Do you have any missing data in between two successive samples? I think no. Now you see here. So in between the successive samples, you will have some gap. In between two successive samples, you will have some gap. Now, what is pi by t? I think you will have some doubt in your mind that what is pi by t? Is nothing but the cutoff frequency. So this is the original data. You should reconstruct from the sample value. So how do you get? Is it possible to get the original data from this? Yes, it is possible. How? So whenever you use low pass filter of frequency pi by t, obviously you should eliminate the higher frequency components, and only you will get this data. In this particular case. And as far as the next case is concerned, the cutoff frequency is far higher. So there is no necessity for inclusion of the low pass filter to get the original data or to reconstruct the original data. Why? range is also has been mentioned. But in sometimes we are regularly using the low pass filter or data reconstruction device to get the original data. That is also very important. So in this case, it is possible to reconstruct the data. In this case also, it is also possible to reconstruct the original data. But as far as the third case is concerned, now see here. So now we see the case. So you miss this data, straight line. So whenever you find this type of waveforms, these are distorted waveform, and you lost the data in between the two consecutive samples. If we select the frequency range is less than 580, the cutoff frequency, So this is the graphical representation for explaining the sampling process. Just by gone through the frequency ranges what we have selected, okay, to get the original data. Okay, those frequencies are very, very important. So always you should remember that the sampling frequency must be greater than or equal to twice the maximum frequency in the same segment. Okay. Now case one, case two, case three. So this is about the sampling. Okay, I require 2 more classes to complete this chapter. That's all for today, and I will give you some time for noting or drawing. See, just draw the waveforms. Case one, case two, case three. So in case three, obviously there is a overlapping of the samples occur. So whenever there is a overlapping of the samples occur, we could not able to get the original data, or we could not regenerate the original data from the sampled sequence. So always you should select the proper values for the sampling rate or the sampling frequency. That must be greater than or equal to 2 into Fm, twice the maximum frequency component in the given signal, right? Okay, students, do you have any doubts regarding this sampling process? Whatever may be the doubt, don't worry or don't hesitate yourself. You just ask, or just you raise your hand so that I will give you control to speak about the doubts clarification. Do you have any doubts? See, I already circulated the second assignment, sorry, first assignment related to this particular subject, and already I have given you my mail also, email ID also. So you can send the soft copy. Soft copy means not typed copy. You just write down on a paper as a hard copy, and you take the photocopy of that hard copy, and you can send it to me. Okay, so that I will finalize the marks. So whenever the college is getting reopened, obviously you should submit the hard copy. Right? Don't you have any doubts regarding this particular topic? Shall I wind up the session now? Shall I wind up the session now? Okay, thank you.